And as it's searching, if ever the path it's looking at ever gets up to that limit in length, give up on it and try a different one. Or equivalently speaking, if it's thinking about what successors, so we have this issue back here, so that this one worked because this state had no successors, and therefore it could go back and look at something else. Then we say, once we get to a certain limit, whether it has successors or not, treat it as if it has no successors. Pretend it has no successors. So that it then is forced to go back and look. These are basically the same thing, just two different ways of looking at the same thing. By forcing it to always stop at some point and go back and look at other options, then we gain, at least to a degree, completeness. By what I mean by to a degree is you need to think about what the limitations are here. If it searches through every possible path, so by applying this limit, it will always stop at some point and go back and look at other options. That means that eventually it will look through the entire search tree, just like that previous diagram showed. If there is a solution somewhere in there, then it will find it. So in that sense, it's complete. A solution within that limited tree, it will find. But if the solution is longer than that limit, outside that tree, it won't find it. So the limitation to completeness here is that we need to set our depth limit properly. To guarantee that it's complete, we have to be sure that our limit contains the solution that we know is there. That can seem silly. How can we know how long a solution is if we don't know the solution? Well, there are two answers to this. One is that for some problems, at least, we can make an argument about the upper limit that a solution could be, the upper limit to the length of a solution. For example, consider our Romania problem. Does a solution that visits the city more than once make sense? For one thing, would it be optimal? No. If it visits the city more than once, that means the solution has some kind of loop in it. If we cut out that loop, then we now have a solution, or we have a sequence of actions that's also a solution, but is shorter than the one we just had. So it can't be optimal. There must be a shorter solution. Any solution that has repeated visits to a state in it also has a shorter version. If we can visit each city at most once in a solution, then we now have an upper limit. The upper limit for a solution is visiting each city exactly once. If we have 20 cities, then we can set our limit to 20. And know that if there is a solution at all, then it must be within that limit. That said, setting the limit that way only gets us completeness. It doesn't get us optimality. If our actual optimal solution were, say, length 10, visiting 10 cities to get to our goal, but the problem I presented is actually shorter than that, but let's just say 10. We can't guarantee that with a depth limit of 20, our search will find that optimal solution. In fact, odds are pretty good it won't. Odds are pretty good that it will find some other solution. And in fact, the solution it gives back to you may have a bunch of loops, or may have a bunch of other work in it that wasn't required. It's a common pattern you may see in such solutions. You play it so you'll be implementing these searches on the homework, and if you play around with them with lengths that are longer than the solution, then you'll probably see this behavior of a bunch of not useful work at the beginning, before at the end of that sequence it may finally have the actual real part of the solution. It basically comes back to the depth first search being able to go the long way around to find a solution instead of the best one. So just setting the depth limit in this way doesn't give us optimality, just completeness. How can we fix this? What do we know about how this depth limit works? In particular, let's think about something. So I've said if the optimal solution is 10, and we set our depth limit to 20, we know we'll find a solution. Completeness. It's guaranteed to find a solution. Not necessarily that optimal one, but a solution. But what if I set the depth limit to 10? The same length as the optimal solution. What will it do? Will it find a solution? Yes. Will it find an optimal solution? What's the definition of an optimal solution? A solution that's that essentially there's no other solution that exists is shorter. I told you the optimal solution is length 10. I set the limit to 10. Can it find a solution shorter than 10? No. Can it find a solution longer than 10? No. The depth limit prevents it from looking at solutions longer than 10. It will find a solution exactly length 10. Maybe not the one we were thinking of as the optimal solution, but it is an optimal solution. Same length as the one we were thinking of. So yes, if we can set the depth limit exactly, then it will find exactly the solution we're looking for. But of course, this is even worse than the argument we had to make previously. To find the optimal solution, now not only do we have to know an upper limit, we need to know the exact length. What good is this? Let me ask you one more question. So we talked about what happens if we set the limit to 10, it will find the optimal solution. What if I set the limit to 9? What will it do? Correct. It will find no solution. If we set the limit to 9, we know there's no solution of length 9. The shortest one is 10. It will look at every path of length 9 or shorter, find no solution. What about 8? Same thing. 7, 6, 5, all the way back to 1. Same thing. For every limit we set that's lower than the actual limit, it comes back and it tells us no solution. For the exact limit we need, for the optimal length, it comes back and gives us an optimal solution. This suggests to us an algorithm we can use to find the value that we need, the limit that we should set. Start at a low value. For example, start at 1. Ask, with a limit of 1, can you find a solution? It comes back and says yes, you have your answer. But if it says no, then you now understand. There's no solution of length 1. The solution must have a length of 2 or more. So what do we do? Well, if it's not 1 and we know it has to be at least 2, let's try a depth limit of 2 and see what it does. If it comes back again and says, well, so if it comes back and gives a solution, then you're done. Or if it doesn't, which for our example it wouldn't, if we try 2 and it doesn't, comes back and says no solution, we know that the optimal solution must be length 3 or longer. So come back and try 3, and 4, and 5, and 6, all the way up to 10. Once we finally try 10, then, again, for this example we're working with, it finally comes back and gives a solution. And now we know not only is that a solution, but because we tried paths of every other length before that, we know that there's no solution of length 9 or shorter, then we also know the solution is the optimal. By trying each of these different depths in turn, iteratively increasing the depth, hence the name, iterative deepening, we can now figure out not only what limit we should set, but we've also gained optimality as well, in a sense. Question?
This kind of sounds like breadth first search.
That's the sense I was getting to, exactly right. Is that the sense of optimality that it's limited to is the same as breadth first search. Breadth first search had that requirement. Remember, it's only optimal in the case that the path cost function is a function of depth in the search tree, of the length of the solution. And this has that same limitation. And for the same reason, breadth first search only looked at a certain depth in the tree once it had looked at all previous depths. And the same is true here. Because we're setting a limit to the depth, each time we increase it, it looks at one lower depth in the tree, and then a further depth, and a further depth. In fact, as we look, so I'll work through this example, I'll show you, then you can see it very much, as you said. Sounds very much like a breadth first search. And it will look like it as well, with a little extra work in between. So we see starting with a depth limit of 0, a solution of length 0. Then it can't even consider the initial state. That would be length 1. So it immediately stops. Length 1. It can look at the initial state, but no further. It immediately stops. A rod is our starting point. It's not a solution. So we have to quit. No solution. So increase the depth limit again from 1 to 2. Now we can look at our initial state, and we can also consider child states, successor states from there. So now we can consider Zorin. But that hits our limit. We're considering a path of length 2. We can go no further, or we would exceed our limit. So now, go back. Now look at City, and then Timisoara in the end. So as you look at this, hitting that limit, we looked at the first level of the tree. For our second limit, we still looked at the first level, but we stopped. And now the second level of the tree. If we continued, if we had increased the depth to 3, increase this to 3, we would explore these, and then from there we would look at these 2, and then go back, because that hits our limit. And go back and look at this, and look at these 4, and then go back, because again we hit our limit. And then look at these and go back. So limit of 3, we've now looked at the third level of the tree. So as you said, it looks very much like breadth first search. And that's why it has similar properties to breadth first search. The only difference being that in between looking at the first level and the second level and the third level, it's re-exploring. It's looking at this earlier part of the tree over and over and over again. You may look at this and see and say that this looks like a lot of extra work. How can this make sense? We already have to spend exponential time searching, and now I want you, or I want us to do even more work on top of that. How can this make any sense? In point of fact, it's not near as expensive as it looks. And in fact, asymptotically, it doesn't even change the expense at all. The extra amount of time we have to spend is actually limited above. It has a maximum value of a constant. I'll show you some examples, but actually it's no higher, it's no worse than 2 times the original cost. And in most more realistic situations, so that's under a particular condition, in more realistic situations, the cost is minimal. You can see that even here. Sure, to get to this third level, it has to look at the entire rest of the tree. But how many things are in this third level? 3, 4, 5, 6, 7, 8. How many things are in the rest of the tree? Just 4. To get to that next level, it only had to do 50% more work, thereabouts.
So is the advantage of this over breadth first search, is it easier to implement, or
Memory cost. This is still depth first search. Memory cost is still linear in the depth that we have to search, versus breadth first search, which is exponential. So we're trading a little bit of extra computation time for a lot less memory usage. No, go ahead. We've already talked about most of this. We're figuring out what depth to use. We're guaranteed to find a solution because we keep increasing the depth until we do. So we'll keep increasing the depth until we find a solution or we run out of time. If there is one, we'll find it, so it's definitely complete. It's optimal in the same sense breadth first search is. If our cost is based on the depth, then it's optimal. But I'll come back to that. Space, as I said, is still good. It's still linear. Time cost or uninformed search, we can't do much about. Although I do have a comment about that. But before that, we can ask. Well, we took breadth first search and turned it into uniform cost search to fix its optimality, to make it more generally optimal. Might we do something similar here? And the answer is, I've seen some examples of this, yes. The primary reason both this and breadth first search have this limitation is because their operation is based on depth. Breadth first search explores an entire level only after it's looked at all preceding levels, depths. This operates by exploring in a depth first fashion to a particular depth before it gives up and looks at other things. It doesn't look any deeper until it's explored an entire tree to that depth. That's why they both have this limitation. So we might consider, well, instead of a depth limit, then let's change it to a cost limit. That should fix this. That should allow us now to pay attention to cost, just like we did with uniform cost search. Take nodes based on their cost. That now we'll search an entire tree, deep enough to stay within a particular cost limit. And that should allow us to find a solution of that cost or smaller. That should guarantee we can find a solution of that cost or smaller, if it exists. Then we just need to think, well, how do we find that cost limit? Can we do something similar to what we did here to find the depth limit? And I've seen examples, yes, of so that would be instead of a depth limited search, we can call that a cost limited search. And instead of iterative deepening search, I've seen examples of iterative lengthening search, or talk at least of examples of it, where we successively increase the cost.